now 1 minute past 2, which probably means we should actually get going. First of all, thank you all for attending. Thank you for joining us today, and thank you for the students as well, or former IfM students now. They're all going to graduate very soon, and will be very much missed in IfM. Thank you all for presenting and making time today. Obviously for you it's a very hard time at the moment, as in finding jobs or starting new jobs, and transition into multiple countries as well. Today basically a bit of an insight into really what I would consider like kind of one of those stories which which is great to tell and great to talk about. But before we kick this off, there's a Q&A function within Zoom, which you can use to ask any form of questions. I will then get those and we will answer those at the end of the presentations. Any questions that we will not be able to answer straight away, we will try and follow up on later on, or directly with you. Or then if you have any questions, of course, you can get in contact with us at any time to actually ask your questions. So what we're going to do today, so first of all, I'm going to give you a little bit of a background about IfM. What is it? What does IfM actually stand for? Quite a handful. And then we're going to go into the 3 topics, the main part of this, where Jack, David, Carl, Oliver, and George are going to basically present about their projects and their work that they've done with the NHS hospitals in Cambridge. And then afterwards, we're going to have a couple of questions, Q&A, and a close. I've just basically Gareth kindly asked a question saying, will this session be recorded? Yes, it will be, and it will be available after as well. It shouldn't incentivize you to just switch off or like kind of not pay attention, obviously. So yeah, what is IfM? And what is this all about? So IfM stands for Industrial Systems Manufacture and Management. While this is a complex name, it's actually very simple. It's an MPhil course, a Master of Philosophy, where we recruit graduate students to join in Cambridge for a year. It is split into 3 parts of assessment. One is lectures and assessments. This is very normal, in brackets, normal lectures as you would assume them to be in Cambridge, very interactive and very much a conversation and a discussion with the students attending. And then these lectures are basically assessed as individual lectures or individual efforts. Then we have something which is very special and different to many other things. We basically have industrial projects, which means that the students and individuals are basically joining, usually in smaller teams, industrial companies. We collaborate and work with many different companies throughout Britain to join them for 2 weeks, usually, or most of the time for 2 weeks, to basically to solve a live project. So a live project means a problem that this company at this very moment in time has is challenging for the students and can be solved within the time frame of 2 weeks. And this is usually something like replanning a manufacturing site or designing a new manufacturing line, but as well strategic problems, very much management problems. They tend to be things as well that the graduates then afterwards in their real life get thrown at and get familiar with. And then finally, there's an academic thesis project, which is 4 months, about 4 months working on a one-to-one basis with a Cambridge academic to basically do research. So obviously, a Master of Philosophy indicates as well that there's a big thesis part in this in the first place. So who do we graduate? These guys that you can see on the screen, and they all have certain like kind of certain aspects in common. Normally, they have a graduate from a good university in the world, or at least had a very high quality result. So they were the best under their team from their university. They usually have numerous backgrounds, so they've done operations management or things that are engineering related. They have a these skills that we basically need as a background, but as well they've got already some industrial exposure, so which is very important for us, because obviously we send them into companies to actually do problem solving. So after this, like, so you're probably asking yourself, what the heck are you doing with hospitals then? The answer is quite easy. Number one is hospitals, from an operation management point of view, are actually engineering problems. So scheduling things which you will normally be like in finding in engineering and in manufacturing, are very much techniques and things that are used in hospitals as well. So when the whole crisis started, I basically had a accidental meeting really with a friend of mine in front of a normal food store in Cambridge, and I said, look, I've got students, if you need any help in the hospital, let me know, because if we can help anything, happy to help and support. So back came a very fast email saying, yeah, I think we need help, or we can do with help. And out went an email to everybody saying who's still in Cambridge and who would like to help and volunteer their time. They very happy to help. And obviously there was more requests than people by the end of the day. But we've managed to put a very, very strong team together out of the individuals that you can see here. Oliver, Carl, Moritz, George, Kaya, Nisha, Jack, and David have been working endlessly hard to actually support the NHS. So as well, thank you to Ajit and Tom, my colleagues, who've been helping to supervise the project. Without them, of course, I would have not been able to stem the work. So basically, next is the three topics. So I'd like to invite the students to basically start their presentations and to take over the screen.
Thank you very much, Florian. So let me share my screen.
Yeah, we can see it.
Okay, so you can see the slides fine, right? Perfect. Thank you very much. So first of all, thank you very much to all the audience for joining us to learn a bit more about the work we've done at Cambridge during this pandemic. So we're going to start with the first project, as Florian mentioned, which is NHS staff testing. On this project, myself, Jack, and Nisha were involved, and we perform a series of projects. And now today we're gonna cover the three main projects. So we're gonna start with project one, which was around layout and process improvements to the testing facilities. Our second project, which was to design and manufacture testing equipment to support automation of testing activities. On project number three, which is the automated planning tool that we developed for healthcare workers screening. So Jack is gonna talk to you first about the first project.
Thanks, David. So our first project was looking at the layout of process improvements on the testing facilities. And this project was based around essentially building from the ground up a testing or a swabbing testing facility. It was to utilize a small car park area in the center of the hospital to allow staff that were both asymptomatic and symptomatic, but arriving by different various transportations, such as car or on foot, to be swabbed. And here at Addenbrooke, we were very lucky. We had around 200 to 300 tests that we could utilize through the university research laboratories. And we'll explain a little bit about the process and the process facility to help support. Here, the slide now, David. So here is some of the process layouts that we helped design. So as I mentioned, we had around 200 to 300 staff needed to swab. And they could both be symptomatic or asymptomatic. And we had sort of three main criteria that we had to meet. We wanted to avoid cross-infection. So that was the risk of people, of symptomatic staff and asymptomatic crossing or meeting or contact with each other. We wanted to make a really easy and intuitive layout, so when people arrived on the facility, they knew where to wait, how to flow through the site, and how to conduct their swab test. Lastly, we had very minimal space. It was a very small area, so we had to sort of maximize throughput by making, best case of every inch of space. So here on the right, you can see a sort of first figure, which was the Addenbrooke's test site process layout. We helped sort of design this and then actually implement it. And then below, using our expertise, sort of a couple of months down the line, we were asked to support setting up the university swab testing site, which doesn't have as many tests, but I think it was around 100 tests per day. And this is just based outside the engineering department, outside the Dyson building. And we used sort of similar principles and civil methods to help design this process map. Okay, next slide, please, David. So our next project, project 2, was the design and manufacture of some testing equipment to support the automation. So project 1 was very much based in the front end of testing at the swabbing stations or the drive-through test sites. And then we had some support through the back end onto the labs. And as I mentioned, here at Cambridge, we're very lucky. We had the university research labs that we could utilize. And you might recently seen in the news that the UK government or the UK are really struggling to meet tests. And this boils down to really a fundamental problem, is that the bottleneck of the testing process is based out of the labs. And many of these lighthouse labs that have been brought online, they were really manned by PhD students and researchers. And as academic institutions and universities have gone back, we've really seen a fallout of all these sort of unmanning of labs. So one of these key projects we looked into really during the peak of the pandemic was to see if we could automate any of the processes. And this is where we helped design and manufacture some key parts in the manufacturing in a pipetting operation that was conducted during the testing. So here it is. It's quite simple. It's essentially some adapter blocks that fit into sample tubes. You can see on the sort of middle picture at the top. And we also helped design some adapter plates for some centrifuges as well, take additional samples. But this is an interesting manufacturing problem. We had sort of 3 criteria here. The part had to be within tolerance, 0.1 mil. It had to be easily decontaminated between uses, had to be really durable, so using multiple cycles. So here we're going to play a little video to show you the operation itself. You can see the reservoir here of the lipase buffer, and that will pipette the solution into the sample tubes, and it's quite accurate. I think within about half a micromilliliter. And you can see that this, you can see a whole batch of sample tubes can be pipetted, and this really alleviates some of the manual processing and manual operations that we were finding in the labs. So that's it. I'll pass you over to David to explain our final project.
Yeah, thank you very much. So our last project was to develop an automated planning tool for healthcare workers. So once the testing pods and labs were established, another issue that we had to tackle was the inconsistent flow of samples from the testing pods at the front end that Jack described before to the back end in the lab. And the inconsistent flow of samples was causing very inefficient use of lab resources. Because they were delivering the samples in different quantities every day at different times. And this was a big challenge for several reasons. Firstly, because the hospital had to screen 16,000 healthcare workers working in multiple wards. And different wards had to be screened with different frequencies based on the risk exposure to the virus. Secondly, through the screening results, high-risk clusters of wards which exposed a high risk of potentially being infected were identified. These wards clusters require rapid testing, and we had to prioritize testing resources for this. And thirdly and finally, we had a third stream, which was the staff who were continuously self-isolating at home for 2 reasons. One, because they had COVID-19 symptoms, and as per the government regulations, they were required to self-isolate. or 2, because someone in your household had COVID-19 symptoms. So this caused a lot of staff to very often self-isolate for unnecessary reasons, and this really reduced the hospital staff capacity. Therefore, testing played a critical role in order to perform PCR to healthcare workers and enable them to safely return to work, as well as screening the hospital to ensure that the PPE is working correctly, that we're protecting the patients, and that we're protecting the staff. So after interviewing some key personnel from both ends, back and front end, carrying out observations and using our industrial knowledge that we learned through IfM, we identified that the root cause was in the testing plan that the hospital was following as a result of the challenges that we described before. To solve this, we created a production planning tool that used a series of algorithms to automatically create the most optimal test plan over a 4-week period. As you can see on the booking management framework on the left-hand side, and the tool used a database with the 16,000 healthcare workers at the hospital who were required to be screened. And then we used a scoring system to prioritize who is getting tested, so which wards will get prioritized. This was based on their exposure to COVID-19, so some wards were required to be tested more frequently because they were continuously exposed to COVID-19 patients, unlike other wards. So based on their exposure to COVID-19 and also on how many days it has been since they last got a test. And this was integrated, and then this later integrated with data from staff self-isolated at home, which also required to have high priority to get a test, as shown in the framework. And then we also integrated this with analysis of the screening results, which enable us to identify high-risk clusters to develop an optimal and testing plan in order to maximize the testing critical resources that we had. So this planning tool helped to establish a stable flow of test samples to the lab and also optimize the critical test resources by 40%. This improved flow of samples also helped to maintain a stable level workflow in the lab and to avoid the lab staff and resources to be either overstrained or underloaded. So here we have some pictures of our time at Addenbrooke Hospital. The bottom left, you can see the staff testing pods in the parking facilities. On the top left, it was myself and Nisa in the clean room in the labs, and then other pictures. So thank you very much for listening, guys. And I believe we're gonna take questions at the end through Q&A. So I'm gonna pass you over to Carl, who's gonna talk to you through the oxygen work that they've done at Addenbrooke.
Thank you very much. I'm just sharing my screen. I hope you can all hear me and see the screen.
Absolutely perfect.
So, good afternoon together. As part of the ISMM students volunteering in the Cambridge University Hospitals Trust, or more specifically the Addenbrooke Hospital, Oliver Lamson, Moritz Meyer-Zuckerker, and me supported by analyzing the oxygen infrastructure and improving its resilience. If we look back to early March, as the number of COVID-19 patients were rapidly rising, the extent of the eventual peak was still unforeseeable. So to treat COVID-19 patients, different ventilation treatments from simple Venturi mask over CPAP to mechanical ventilation were used. However, the UK only had about 8,000 ventilators available, while the NHS predicted a need of up to 30,000 ventilators at the peak, which was later then lowered to about 18,000 devices needed. However, while procuring and manufacturing additional ventilator devices was at the center of government and media attention, more is needed to safely and successfully ventilate a patient. And that includes a fully equipped ICU bed, medical staff, and then medical oxygen. And since some of the NHS trusts experienced serious issues with their oxygen supply in early April, and even before the UK peak of COVID-19 patients, our focus was put on the medical oxygen supply in Addenbrooke Hospital. So with those problems arising in the different trusts, NHS England issued an alert with urgent actions for estates and facility departments. And these included determining the maximum flow rate of oxygen supply and any limitations to the oxygen delivery, which might be the pipework architecture and anything like that. And then if we're looking at how to approach this, to begin with, we can look at the situation around oxygen infrastructure, describe it by an analogy to a water tap. Who questions and investigates how much water is behind the water tap? It just works until you face a drought. And to understand and analyze a completely unfamiliar and quite complex hospital oxygen infrastructure without any prior experience in the field, we build on some important capabilities such as structured problem solving and a hands-on approach, and at the same time, specific engineering knowledge such as fluid dynamics and data modeling, very useful in the kind of course of our project. And at the start, we divided the challenge in demand and supply side. And then on the demand side, it was about determining the maximum number of beds with oxygen outlets, looking at forecasts of patient numbers and estimating the average oxygen consumption by a patient. Whereas on the supply side, it was about determining the maximum capacity and the potential bottlenecks in the supply and distribution system of the oxygen infrastructure. And since there was no single reliable method to monitor the usage of oxygen across the entire hospital, analyzing and comparing the available monitoring data was another important task, which Oliver will now talk to you about. Having said that, actually, I'll hand over to Oliver, who will present you our work in a little more detail.
Thanks, Carl. So as Carl has given an overview of what we were dealing with, basically, first of all, for us from a project perspective, if we actually wanted to dive in and figure out how to tackle this, on the supply side, we needed to develop some sort of central cohesive understanding of the hospital supply capacity. So for our purposes, when we say supply capacity, it's basically maximum flow rate in the pipe network for the hospital. So how much oxygen can we actually flow through this network? So without getting too technical, we effectively started from a very high level view and then zoomed in as important areas emerged. So in this case, it meant first understanding the central supply plant. So it's basically just a large liquid oxygen storage tank, and then there's a vaporizer and a control panel, which you can see on the left there. And then this can give us the total system capacity, but it doesn't actually tell us much about whether the pipe network is able to deliver the flow rate that we need. So we moved on a sort of a level deeper to understand the distribution system. So first of all, the hospital supplied us with lots and lots of these huge A0 sheets, an example of which you can see up on the slide, which were the schematics of the system at some point in the history of the hospital. But unfortunately, these plans were unclear or outdated or incorrect in places, which obviously just happens when you're running a 1,000-bed plus hospital. And then that meant we actually had to spend a few days in the basement of Addenbrooke's physically confirming pipe layouts. So you can actually see me there with one of the guys from the estates team who were very helpful in getting us to understand the hospital layout. And then to correct these plans, we used valve locations as reference points. And then this also allowed us to do something convenient, which was transfer these abstract schematics over to physical blueprints. So then finally, taking that very complicated schematic, we did what any engineer would do, and that's simplify the distribution plan. So we could actually calculate some pressure losses in the system and give us some indication of flow rate limitations. Now, at this point, we were fairly comfortable that the central supply system was robust. In other words, we could deliver the maximum flow rate out of the supply tank and vaporizer. And the design is this ring you can sort of see on the map there, which maintains pressure centrally. But we really had to, but we'd actually been part of some physical system tests on our first day, literally the first day we walked into the hospital. And those had set off alarms, and we knew that we hadn't gone over the whole system capacity. So at this point, it was appropriate to get maybe a bit fancier. And Maritz, who's our team member who's not with us today, simulated loads at the ward level on the branch pipes coming off the main ring, and was able to replicate what we saw in testing, which gave us confidence in the model's ability to reflect reality. And the information this effectively gave us was that wards sharing a branch off the main ring were more limited in maximum supply, especially the older wards, which had smaller pipes, which is quite an interesting insight because for the hospital, that means that the wards that you plan to have a lot of COVID patients in, because you want to stick them all together so they don't infect everyone else, were not necessarily the most suited just from an oxygen supply perspective. But of course, in planning your bed layouts, you have to balance between infection control and clinical interests and the estate's interests. But at least we were able to understand how much oxygen we could supply. Moving on to understanding how much oxygen we were actually supplying now that we knew how it worked. There's this old operations management aphorism, which is if you can't improve what you don't measure. So effectively, we needed some way to measure the oxygen supply within the hospital over time. Since we didn't have any flow rate sensors, we'd have to calculate the usage somehow. And the first and most simple approach was to use, we had the tank volume versus time. And you can look at the decrease in the volume, and that gives you how much usage you've had over that period of time. But you immediately run into some issues with the sensor being highly inaccurate and noisy. You're basically using it for what a job it's not supposed to. And over a period of about less than a week, the sensor can't give you much useful information because you have to smooth it so much. Again, to use an analogy, it's sort of like trying to figure out how fast your car is going by looking at how quickly the fuel needle's dropping. So technically you can do it, but you probably shouldn't, and you also can't really trust it. So you have to take a different approach. So the alternative approach we came up with was determining oxygen usage from the clinical treatment system, which you can see is the bottom left edge of that triangle. That tells us how much oxygen is supposed to be delivered to patients at any point in time. Unfortunately, this relies a lot on manual data entry, which particularly for nurses is very difficult in the midst of an unprecedented pandemic. We had the added issue of every time we exported data from the hospital's central system, it seemed to change historically, which meant it wasn't consistent, which also led us to question the trustworthiness of the data. And then finally, the usage numbers we were getting from the clinical treatment system for oxygen delivery were different to the ones we were calculating from the tank volume. So you have these two different numbers and you have no way to know which one is right. So the only real solution for us was data triangulation. We needed some sort of third source to bound this real world value. And on the right there, you can see the control panel for the oxygen delivery system. And what we ended up doing was installing a flow meter, quite a fancy one actually. It's quite interesting technology, an ultrasonic flow meter. So we didn't actually have to, it wraps around the pipe instead of actually having to be physically installed and having to block off the system, which is of course impossible in these times. And in the end, it just meant for us that we could clearly see the oxygen system's total usage at any point in time, which would mean the hospital could see their usage and if it was getting close to the limits, and would be able to react accordingly and have warning. I'll hand back to Carl now for the wrap up.
Yeah, to summarize our experience working on the oxygen infrastructure for Addenbrooke's, we can look at three takeaways that we conclude. So firstly, with the inaccurate and outdated information on the legacy infrastructure, questioning the obvious was quite important. So the NHS England-wide alert, which was issued about a week after we started working on that topic, showed that such crises uncover very unexpected system issues. And secondly, with the uncertainty and stress in such crisis situations, designing and following a well-structured approach is key to uncover all potential bottlenecks in the systems. For example, while the primary focus was to increase the number of ventilators in the UK, Addenbrooke's may have struggled to run all available ventilators in the hospital simultaneously, depending on the base load. And with the diligently analyzed systems, you can base those decisions about patient capacity or emergency plans, and you can ground them in previously unknown factors. And then lastly, for systems that appear to have plenty of overcapacity, having a reliable usage visibility is very important for the resilience in crisis. As we have seen with the car speed analogy, a deep dive into the available data can reveal unexpected inaccuracies. So therefore, digitization of such legacy systems can really enable triangulation and live usage visibility. So thank you very much for your attention. If you have any questions, please feel free to write them in the Q&A function at the bottom of your screen. And I'm going to hand over to George, who will be telling you about capacity modeling.
Thank you very much, Carl. I hope you can hear me, guys. So thank you very much. In the coming 10 minutes, I'll explain to you what kind of project we've been working on together with Kaya Dreesbijmdijk and Dr. Ajit Pardakat over during the first wave. And actually, we're still working with Addenbrooke's hospital currently in order to provide predictions for the second wave. So we've been looking during the first wave at the capacity requirements by COVID-19 patients in the hospital. And then with resources or with capacity, we're talking about beds, oxygen, ventilators, and all these kind of scarce resources. So if we look at what is happening, what was happening during the first wave is that we see a large influx of patients, but with an uncertain pattern. So we don't exactly know when those patients are coming in. And of course, on the right-hand side of the slide, you can see those graphs we've been seeing all over the news based on the R0 rate to determine when are patients coming in and how many are coming in. And in the end, the question is, how many beds are actually going to be used? How many resources are going to be used? So this project was really about transforming those graphs on how many cases do we have a day or how many hospital admissions do we have a day, and transforming those figures into actually how many beds do we need, such that Addenbrooke's hospital was able to really prepare for such numbers. So if I'm talking about different scenarios and different waves, if we actually now look at the second wave, in June we made the second set of predictions and the second set of scenarios together with a team of virologists in Addenbrooke's hospital. So on the right hand side, you can see the graphs we've been seeing in the news as well. So in the dark blue, we can see the actual number of hospital admissions during the first wave in Addenbrooke's hospital. And in dark gray, the predictions for the autumn 2020 made in June, and we're now actually adapting those scenarios slightly since the second wave has basically started. So the team of virologists created 3 different scenarios ranging from an optimal or best case scenario to a worst case scenario, where the base case scenario, so the orange scenario, is based on the first wave that Addenbrooke's observed. And so we're using those as an input to the model we have created to really determine how many beds do we need and all the other resources I've already mentioned. And how do we do that? We basically simulate how every individual patient moves through the hospital and subsequently makes use of resources along the way. So for example, imagine you show up at Addenbrooke's hospital with COVID-19 and you will require hospitalization. Then you can either have a complicated stay or an uncomplicated stay, as we name it. So either you will require some form of critical care or intensive care during the stay, and usually you always need some form of general ward care, as we call it. And then, of course, hopefully the patient survived and gets discharged, or is transferred out to a different care facility or care home. And of course, there's a possibility that the patient does not survive. And so what we do is the model that we've created really looks at all the different possibilities of patients moving through this network based on data we gathered from hospitals in China, Italy, and also on other hospitals in the UK. And roughly halfway through the first wave, we were able to also make use of data from Addenbrooke's hospital and the patients which actually were admitted to Addenbrooke's hospital. And so what we did is we built a simulation model and then mapped those patient flows and also mapped the resources which those patients require So for example, you can imagine that in critical care, in a critical care unit, you will need a ventilator and you will require more oxygen. Whereas on a general ward, you might have periods where you actually don't need oxygen, or and of course you won't need a ventilator. And that of course determines how Addenbrooke should be prepared for the first wave and now for the second wave. And then it's really important to understand not only how those patients move through the system, but also how long they stay in a certain phase of their journey. So on the right-hand side of this slide, you can see the different phases of a patient flow, and how many patients actually spend how long in the hospital. So for example, the bottom left graph shows the length of stay of a patient in the intensive care unit. And it really shows that the length of stay is extremely variable. So roughly 80% of the patients spends 1 to 4 weeks in critical care if they require critical care. But there is also a group of patients who will need significantly longer and might even spend 2 months on critical care. And it's really important to therefore not only work with the mean length of stay, but actually use with the entire spectrum of different length of stays a patient can have. And that's why we use the simulation model to help Addenbrooke's Hospital to really accurately predict how many resources a patient needs. So if we look at briefly look at the validity and the accuracy of the model, we see that actually a simulation model performs better than a deterministic model. And with deterministic, I mean where you do not include that entire variability, and it actually quite accurately matches what happened in Addenbrooke's Hospital. But the most important conclusion, or the most important benefit from using such a simulation model, is that we were able to map such a wide variety of hospital resources. Because of course beds are important as a resource, but on the other hand, you will need the entire range of resources to really cure the patient. So you will need oxygen, the ventilator, etc. And the simulation model helped us to predict on a wider range of resources than usual literature models provide. So if we then briefly show a snapshot of some predictions that the model provided, we can see for general ward beds, so we call them gym beds, we see for different scenarios the different results that the simulation model provided. And we've run the model a lot of times to really capture that entire spectrum of variability. And with that, we were able to actually say to Addenbrooke's Hospital, you will need, for example, so whereas other models say you will need 200 beds during the peak, we were actually able to say, well, you might need between the 200 and 300 beds with a 90%, within a 90% confidence bands. And so that also helped Addenbrooke's to see what the range of variability is and to what degree they wanted to prepare for a worst case scenario. Well, the same happened for intensive care. And the interesting thing, and the same conclusion holds for the general ward beds, is that the worst case scenario, so the red scenario, compared to a base case scenario, so the orange scenario, that the number of admissions during the peak day is twice as high. So a base case during the peak day, 16 admissions daily coming to the hospital, and roughly 32 during the worst case scenario. But if you then look at how that translates into the required beds, we see that you need far more than twice as many beds. And it also shows the importance of not only looking at the graphs on the number of daily cases, but also to look at the actual resource consumption. And of course, this also shows the huge surging activities which were required by Addenbrooke's Hospital to make such capacity available for COVID-19 patients, because those levels are significantly higher than they observe normally on critical care. So if we conclude this, what have we done for Addenbrooke's Hospital is, so we've looked at those variable arrivals, the length of stay and the patient flows of COVID-19 patients, and try to transform those graphs we've seen in the news on the number of daily hospital admissions and transform them into predictions on scarce resources, and evaluate if the supply and the demand of resources actually match well, or if we need to upsurge some resources in the hospital. So, for example, one of the conclusions was to Addenbrooke's hospital is that critical care really forms a bottleneck, and that it's really important to create more critical care beds and the required staff, which of course belongs to that. But there were also some good news, good elements to it for Addenbrooke's hospital. For example, the number of ventilators were theoretically predicted to be sufficient throughout the wave. And it also helped Addenbrooke's hospital to prioritize on which resources they should focus with their, of course, limited time available. And in the end, and that's also for the second wave we're helping them with now, it allows them to prepare for those different scenarios. And it also shows the importance of being able to flexibly up and down surge capacity in order to really optimally treat not only the number of COVID patients, but also the number of non-COVID patients whose care has not stopped, of course, during the COVID-19 wave. So thank you very much. I think I will be handing over to Dr. Florian Metzer now, and I'm happy to take any questions afterwards.
Now I just have to find my unmute button. There we go. Perfect. Thank you very much to all of you for your kind contributions to this. I've got plenty of questions really, so some of them we're probably going to have to ask later. I believe this will go to Jack and David. On the hospital testing, I can see how the algorithm in project 3, which basically means the testing throughout a wider hospital, prioritizes tests, but I'm unclear how smooth the flow of the lab was. If you want to comment on that.
Yeah, that's a very good question. Yeah, so there was not enough information, I think, on the slide maybe to understand how, but basically, when we did testing in the hospital, there was 2 streams of testing. One was the testing pods, where people come in to the pod and swab. These were usually people who were self-isolating at home. They drove to the testing pod for a swab, and then it was collected. And then we had a second stream of testing, which was screening wards. And how this worked is the day before the test, what we did was we gave the samples, the kit samples to the wards the day before, and then the day after they swab themselves, and then we collect the samples. So how this helped to smooth out the flow was by coordinating both things: the test samples taken on the day, but also coordinating those samples that we're going to receive 24 hours later. And on top of that, coordinating all the wards and making sure that every day were there 2 collections, 90 samples in the afternoon and 90 samples at the end of the day. And that way the lab knew how many samples to expect, and they could run the qPCR machines at full capacity every time. I hope that answered your questions. Yep. It was really around coordination.
Perfect. I think one addition to that is that the university lab was obviously was partly as well staffed with PhD students and very highly supportive individuals that basically worked as well very hard to get these tests done. And of course, if you're receiving tests at any point in time throughout the day, and sometimes 7 o'clock in the evening when you're actually preparing to go home or basically do something else with your life, and then that can be slightly frustrating when you're volunteering your time. So this was as well, therefore the human side, so to say, was as well addressed throughout through this project. Another question for you guys: what kind of improvement would you suggest to this current bottleneck situation, which makes it unattainable to utilize testing capacity? Highly political, I'd like to say.
I think I'll go ahead. I think I'll go ahead and try and answer this question. So this really brings us on to our project 3 of the testing, which was creating a production plan to really utilize this capacity. And what we were finding is that there was an inconsistent flow of samples, as David has rightly pointed out, going from the front end to the back end. Now, the key bottleneck in the lab in the back end is the PCR. It was the polymerase chain reaction process machine that can be up to 2 hours long, and this runs in a batch processing format. So it's a 96 well plate. You load up the 96 wells, put it into the machine, and then you run the process for 2 hours. What we were finding is that that process could sometimes be half filled, a quarter filled, and this was due to that inconsistent flow of samples. So that's really where David and I and Nisha started to develop this production planning tool that would really smooth out this flow and bring consistent batches to the labs. Ideally, you want to be running 96 wells on the PCR. When that's running, you're then preparing the next batch of samples to the PCR, so you get that continuous flow. So that was really trying to utilize the capacity as such. But if I may add to that, if we really wanted to up the capacity, we needed essentially more labs, more personnel, and one key thing that's not very highlighted very much in the news is the strain officers. So you can imagine the whole world trying to get the supplies and resources needed to conduct these tests. And some of the key parts of the process, or some of the key inputs to the test, such as small sample tubes or even swabs for that matter, are critically short worldwide. So you can imagine there's a big constraint of resources there. So if we wanted to really up the resources, we need to have to find or potentially increase the production on that side.
Perfect. Thank you very much. For Carl, maybe, or Oliver, oxygen supply modeling and measurement was quite interesting, potentially good model to share with other NHS trusts in their ongoing preparations. How is this case study information being disseminated for wider benefit?
Yeah, so I'll take it. So we actually, during our time doing the project, already had a meeting with and presented our findings to an authorizing engineer who is in charge of multiple NHS trusts, oxygen supply, and other medical gas supply in general, and in terms of authorizing and commissioning them. So he's already had the information and disseminated it to the other trusts he's involved with, and as well as the board of authorizing engineers that he meets with. We've also written somewhat of a white paper, and we're still in discussions for wider dissemination of that paper. There's some findings we need to confirm and some things to include in it that aren't yet there, but we are in discussions for wider dissemination of this work, because we do think it should save other trusts quite a lot of time and quite a lot of legwork if you can start with the conclusions.
Perfect. Thank you very much for this. Alan, who asked the question. So if you've got some pointers for, or if you would like to have the report, obviously we can make that accessible as well. From Gareth, a question: how do you model a second wave? Is that from epidemiological models, behavioral models, political models, and so on? What's the impact, George, for you?
Yeah, that's a really interesting question, which we've been struggling with for a very long time, basically since the start of COVID-19. And a lot of papers are being published which provide some sense of direction. But in the end, it's also that a lot of those epidemiological models are based on the assumption that you, in the end, reach herd immunity. Or that you know what the effect of non-pharmaceutical interventions, such as lockdowns, what the effect of that will be on the R rate. So in the end, we are using both those models, but in the end, we always change those models in order to actually simplify them and to tailor them to the Cambridge region. Because of course, all these models, also the first slide I showed with all these different curves, they are perfect curves, but actually what you see in reality is that and also in the US, for example, a curve can consists of two separate curves. And actually, you will need to really understand the demographics, the society, the behavior within your region to really understand what will happen during a second wave or during the first wave. So what we've been doing now for the second wave is we've been looking at the first wave and basically making adaptations based on that. So it's based sort of the anchor and adjustment approach. And so that's what we've done in June. So we really did the anchor and adjustment approach. We took the base case scenario as the scenario we observed during the first wave, and we made two scenarios besides that. But actually now we're starting to look at what will the number of cases in the society, how will that translate back to hospital admissions? And that's completely different now than compared to during the first wave, because now we're testing much more, and in Cambridge a mass scale student testing program is set up as well. So a lot more cases will be reported, but actually the amount of hospital admissions will be related differently. So it's a bit of a lengthy and vague answer maybe, but we're still in the process of trying to find out how, with the increased number of positive tests which will be collected, how will that translate into actual hospital admissions. But in the end, the short answer is the epidemiological models are really interesting, but predominantly on the national level. As you've seen in the graphs I showed, the peak day were 20 people a day. On those small numbers, it's really difficult to use such robust models.
Thank you, George. I think there's two more questions that are in that direction. What is the chance of for example, third wave or even more? And then what is has a second wave already started? I think one of the takeaways of this is that probably, as well as a society as a whole, we have to learn to live with the fact that we won't know everything ahead of time, as in there's not an answer which is 1 or 2 or 3, but we will have to learn as well along the way and basically get more insights as we're learning about this very new virus, and let the virologists as well do their learning.
So to briefly answer that one, so the third wave, Harvard and Imperial College are both published papers which were actually predicting multiple waves based on the assumption that there won't be a vaccine available. And even they made models when assuming that the vaccine might, for example, only work with a 50% effectiveness. But it's really hard to look beyond the second wave because it will depend on when a vaccine will be available. And that would be mere speculation from my side if I would comment on that. But if there won't be a vaccine and the country won't be in full-time lockdown, it might be hard to, and there are no optimal treatments available, it might be hard to not get a third wave. But as mentioned, it's based on a lot of different factors besides epidemiological models alone.
Yeah. There's another another question for the testing team. The question regarding the plan developed for staff testing: is there a risk that the demand for urgent top priority testing outstrips demand, assuming not enough tests are supplied? Would your model be able to adapt to this eventuality, and is there a risk of this shortfall materializing during a second wave? Maybe David or...
David, so try and answer part of that and you can answer the second.
Yep.
Okay, I think I've lost David. So the first part is that we did have a batch of tests allocated each day for urgent response. And that was sort of fudged into the model to allow urgent testing required. But if those urgent tests weren't utilized, then the highest priority of wards, so i.e. the highest risk wards, what we defined as red wards, which were COVID-related wards, they would fall into those allocation slots. So every day we were maximizing utilization, which was about circa 200 to 300 tests per day.
Yeah, that was something that we planned for the model to be easily modified, so we can easily modify the model. Because, for example, when we gave away the wards, the samples to the wards, not every person in that ward was going to swap and return the test, because the PCR, the swab test on the nose was very painful, and some people were not happy every week. So we saw that the return of the samples was around 80%, so 20% on average of every ward was not swabbing. So we had spare capacity there that we could use. And what we did is in our model, we factor for that in order to make sure that those spare spots available could be utilized on the day.
Perfect. Thank you very much. Two more questions maybe, and then we're probably going to have to draw to a close. How might the demand and capacity model be used effectively? Can we use this data beyond the pandemic? George, I think that's for you.
Yeah, so we are indeed trying to make this model publicly available. So we're in the middle of a process of trying to publish it together with a virologist in Addenbrooke Hospital. But the question is, I think, more on other pandemics as well, so beyond COVID-19. And so that will really depend on what that pandemic will look like. But in general, the model says that a patient can either go to a general ward or will go to a general ward and might require intensive care. And that is basically a sort of general process a patient might be going through. So in that sense, the model will be able to provide benefit from other pandemics as well. But what, for example, is not included in the model is readmissions. And that will also, time will tell if the model will need to incorporate that. With COVID-19, it's still not clear if you can get it a second time for sure. And if you will get it less severely, and you might not need a second readmission to the hospital. But in case another virus will need a lot of readmissions, then this model will need to be adapted. But in general, this model is able to provide benefit beyond COVID-19. Yes.
Yeah, fantastic. We're slightly running out of time. I would like to finish on time, but from Brian, I think more a comment. Very interesting. Thanks for your insights. Who in the hospital is responsible for acting on your findings and both testing and resource use? Hopefully, the CEO has your work on every board agenda with a senior board member taking responsibility. Maybe you can like kind of all share a little bit of insight on your experience on this.
Yes, thank you for that. On our side, there was a guy called Mike Weeks, who was actually a clinician at the university, who was in charge of the whole staff testing. And yeah, I do believe he was taking our suggestions and future improvements to the board, but I think on the background, there was a lot of politics involved that we didn't get involved with. We just focused on the operational and on the...
I think
what could be done on the spot to have a direct impact.
Maybe just to walk through the project, Oliver, briefly.
Yeah, so I think all of our projects had quite senior or very senior stakeholders, various directors who were fell right underneath the CEO on the hierarchy, as well, and were attending and presenting various bits of our work to the board. Obviously not wanting to take up too much of their time. The hospital was also super welcoming to us. On our first day we arrived, the CEO actually greeted us all and was very excited to have us there. So everyone definitely our work was definitely picked up and actually used. It wasn't sort of just done as an academic exercise.
Yeah, fantastic. Thank you very much for all the questions, for all the work. I hope that my screen is now visible again. Oliver, Carl, Moritz, George, Kaya, Summer, and Nisha, who basically can both not be with us today. Jack and David, thank you so much for your hard work. There were a couple of thank you notes as well in the question chat, and notes of appreciation as well. Thank you to all the NHS staff. As we said, like, you know, if you're working hard, like, kind of, which the last question basically referred to as well. Sometimes there's a human side to it. It's not always nice to be told that one is wrong, or then that one is right, and to have this high speed of learning. We at all times felt absolutely welcome, actually very highly appreciated by the NHS, and the uptake of most of the suggestions was super extremely high, and it was relatively fast, for a large organization like this, at all times very fast, changed and supported. So thank you to all the NHS staff. We've basically talked to the board directly as well. The CEO of Addenbrooke and a board member were involved as well, to ensure that all the students who are involved, so the IfM got a presidential award from the Royal Academy of Engineering. So all the individuals involved in this were named on this award as individuals, and therefore to show the appreciation as well. So you're actually looking at medal winners, so to say, as well. And thank you very much for your time, and thanks to all the students involved. Bye-bye.